כנראה צריך להקליט, כאילו...
מה זה?
אני שואל את הבחור שמקליט בדרך כלל.
לא יודע איך עושים את זה. היה פה איזה אירוע.
כן. אני מתקשר עליו.
או שזה כבר מקליט, כי יש...
מה זה?
לא, זה פייק.
כן.
אתה יודע איך מפעילים את הדבר הזה? כן, סליחה. שלבים בשביל שאני... רגע, יש לו שם איזו הודעת...
לא, זה של הטלוויזיה.
של הטלוויזיה, אוקיי. Fine. So, today we are going to start with the topic of global analysis, as opposed, as I already stressed, to the local analysis we dealt with so far. So now we are doing global analysis. Okay, and I will start by trying to stress the differences between global analysis and local analysis. In particular, the main the tool of global analysis we are going to deal with in the next lecture is perturbation theory. Okay, so let me try to explain what's the difference between global and local analysis. So you remember that up until now we had an equation like area equation y double prime equals xy, and we wanted to analyze it around some x naught. For example, x naught is 0, and we expand it as a power series, and x naught is infinity, where we were using all the mechanism of asymptotic analysis, right? But this is, we looked around a certain point, and we wanted to analyze the solution for this equation around this point. This is local analysis. When local analysis fails, so clearly local analysis becomes problematic if we want, for example, to solve a boundary value problem. So if we want to solve this equation where y of 0 equals, I don't know, 1, and y of 23 equals minus 4, right? We can try to solve the equation with boundary conditions, and clearly we cannot use local analysis. Local analysis only tells us what's going on here. But now I want to make a connection between what's going on here and what's going on here. And this is completely a different task. So to solve problems that have to do with boundary conditions, we should need some other method rather than just trying to explore the behavior of the function here or the behavior of the function here. We want to get some approximation that will be sort of not necessarily uniform, but will be valid to all this region. Okay? And the way to do that is to use perturbation theory. So instead of local analysis, which is an analysis around the point, right? So the question is, what is a small parameter? Yes, this is a general question in physics. What is a small parameter? So here, the small parameter is x minus x naught, right? We analyze the system in a way that assumes that x minus x naught is small, and we write a power series or whatever, right? Now the small parameter will be a parameter that we will introduce, and we call it epsilon. Okay? let me start by trying to explain what's the difference between, to contrast the local analysis with the global analysis. So I would like to deal with a very simple equation that is, I mean, simple in form, but of course, that is y double prime is f of x y. Okay? This is a, you may think about it as a general Schrödinger equation, right? You have psi double prime and some potential times time, psi, right? And you can absorb the energy into the potential. So this is a very, I mean, this is, although it looks like a simple equation, it clearly do not have general solution because we don't have general solution for the Schrödinger equation. And although I'm not going to solve boundary value problem, but just in order to stress the contrast between the local analysis and the global analysis, I would like to solve the initial value problem. So I want y of 0 to be 1 and y prime of 0 both to be 1. Right? So this is an initial value problem. And now I would like to solve it for every x. Okay? See what I'm trying to do? Good. Now, so for example, just to give you intuition, if f of x is x, then this is the equation that we know and love, right? But you can put it whatever you like. X minus x cubed, e to the x, whatever. Everything that you are happy with. Okay? Good. Now, what should I do if I want to do a local analysis? So now I'm not doing anything new. I'm just reminding you what is the general program that we already have. So in local analysis, we assume that y of x is actually the sum from n equals 0 to infinity of a n x to the n. And if you want f of x, maybe everything, but let's write f of x in the most general form, a sum from n equals 0 to infinity, m equals 0 to infinity, just to, right? Of fm x to the n. I mean, right? And now I can, so what is y double prime? So y double prime, this is a0 plus a1x plus a2x squared, blah, blah, blah. This is f0 plus f1x plus f2x squared, blah, blah, blah. Okay? And now what is this equation? This equation, okay. What can we say from the initial conditions?
A0 is, you can estimate the value of A0 and F0.
And?
F0.
Why F0?
No,
These are two conditions on y of 0.
A0 and A1.
A0 is what?
A0 is 1.
Is 1, and A1?
Also 1.
Also 1. Thank you very much. So A0 is 1, and A1 is also 1. This is here, and I satisfied the initial conditions, right? Now, I would like to write the equation. Now, what is y double prime? Clearly, the derivative of this is 0, and the second derivative of this is also 0. So y double prime is actually 2a, 2 plus 3a, 3x plus 4a, 4x squared x.
Wait, no, shouldn't it be 6?
No. 2a2 plus 6a3 x, right? Plus 12a4 x squared, and so on and so forth. Okay? This is equal to what? To f times y. So I have f naught plus f1x plus f2x squared. Again, only the beginning of the series. Times what? Times 1 plus x plus a2x squared plus blah blah blah, which is equal to f naught times 1 plus f1 plus f naught times x. You see, this times that and this times that. And now if I want the x squared, then I have plus f2 plus f1 plus f naught a2 x squared, and so on and so forth. And what is local analysis? We are now going to say that this, right, is equal to that term by term in x. Okay? So we will find, so these coefficients are given because f is a given function. Okay? These coefficients are given. And once these coefficients are given, we can solve. We can say that now 2a2 must be equal to f naught. So a2 is f naught over 2. And now we have 6a3 must be equal to what? To f1 plus f naught. But f naught is yes, that's it, right? So a3 is f1 plus f naught over 6. Okay? And then we have 12a4 will be equal to f2 plus f1 plus f2 times a2. But a2 is f naught over 2. Yes, and so on and so forth. So we can find all the coefficients one by one. Note that I always have only one.
Shouldn't it be f naught squared over 2?
F naught. No, a2 is f naught over 2.
Yeah, and a2 times f naught is in the other term.
Ah, sorry, I have, this is f naught. This is not f2, this is f naught.
So it should be f naught squared.
Yes, so f naught squared. Yes. So, but the point is that you have only one variable to decide about in each equation, right? Because here, you know f0, you have to find the a2, right? Here we know f0 and f1, so we find f3. Here a4 depends on a2, but we already know a2. So we don't. It's all very simple algebraic equation, and by turning this machine, we can solve for all the power series if we have infinite amount of time, at least, right? So this allows us to calculate to solve this equation by local analysis. You see, we started with at 0, and the small parameter is x, which is the distance from 0, and we are doing it term by term by term by term, which is what we did until now. Now, what will be the what limits the feasibility of this approach?
Well, there's the fact that f naught has multiple terms. It can have more infinite terms, just like it just makes as you get to higher and higher terms in x.
Okay.
More complicated.
No, but suppose I have infinite calculation power, right? I'm Laplace demon, right? What will limit this approach? Clearly, suppose now that f of x is 1 over 1 plus x.
So it'll only be correct in the.
This is the problem. I cannot use this expansion for x larger than 1. Right? This is what we we wander around in the last 2 lectures. I don't have power series. So I cannot solve, no matter how much effort I will put in this procedure, I will never be able to get above x equals 1. Right? So I'm limited by the closest singular point of f, by the radius of convergence of the Taylor series for f. You see? Okay. So this is the problem with, I mean, an example for a problem that may happen in local analysis. Okay? So now, what we would like to do. So suppose we want it for x equals 5. We can't use local analysis. So let's try global analysis. Global analysis is based on a very simple approach. I guess this is most erasers are in a bad shape. Sorry. So now we are doing global analysis. Here is the trick. This will be our small parameter, epsilon. We write epsilon, and epsilon will be from now on our small parameter. Right? So our series will not be a series in x, in the distance from 0, but our series will be expansion in powers of epsilon. So we are going to assume only one assumption, that we are going to assume that y of x is a sum from n equals 0 to infinity of epsilon to the power of n yn of x. So now we have the coefficients are not powers of x, but functions of x. You see? For example, I mean, to understand this, if there is a chance to understand it anyhow, it only through examples, right? So again, I'm going to this example. Again, the trick should be to solve it term by term, and in order to do that, the zeroth order term must be solvable. Otherwise, we cannot do anything, right? So the zeroth order term, what happened when epsilon, the zeroth order term, right, is not epsilon to the power of 0. The zeroth order term is what?
Why is it?
What I did here?
It's y equals
Yes.
ax.
Okay, so suppose I'm taking only order 1 term. So I neglect every term that have epsilon, epsilon squared, epsilon cubed, blah, blah, blah. Yes? What is the equation?
It's just with the y0, right?
Y equals a straight line. Y equals ax.
Y and x.
What is the equation? This is the equation with the epsilon.
Oh, it
Y
equals
double
I'm
times
doing the
y.
the second
expansion.
derivative of y
Right?
equals 0.
The organal
What is the equation?
The same equation.
fxy.
No,
Oh.
0.
Y prime equals y squared, right?
No, y prime prime
Why?
equals 0.
Thank you very much. Y double prime of x equals 0. This is y0. This is y0.
Oh, it's not epsilon in the power of 0?
Yes, it's to zeroth order in epsilon, meaning that you have, you see, you have terms that are proportional to 1, so
1, yes.
terms proportional to epsilon, terms proportional to epsilon squared, and so on and so forth. Now I neglect all terms that have epsilon in them. So I'm taking only order 1 terms. So the only order 1 term, or if I'm neglecting everything that have epsilon, then clearly I should neglect that. Because everything here, no matter what, will be multiplied by epsilon. Okay? So I have y naught double prime of x equals 0. That's the first equation. What is the solution for this equation?
Y equals ax.
Y naught is a plus bx. That's a general solution. But now we have to take care of the initial conditions, which means that it will be 1 plus x. You see? That's it. So this is the solution of the equation to zeroth order in epsilon. To zeroth order in epsilon, this term do not exist. Okay? Now, what will be the equation to first order in epsilon? maybe I will try to facilitate the equation is sum from n equals 0 to infinity of epsilon n times y double prime n of x is equal to epsilon to f of x sum from n equals 1 to infinity or 0 to infinity of epsilon to the power of n plus 1 y n of x. You see that this and that equation are the same? Okay? Now let's write the first few terms, as we are doing with power series, just to get an intuition, right? So this is y naught double prime plus epsilon y1 double prime plus epsilon squared y2 double prime, and so on and so forth, equals to epsilon y naught f plus epsilon squared y1 f plus epsilon cubed y2 f, and so on and so forth. You see, here are the first terms in this side and on that side. Are you with me?
Yes.
Good. So now we start to collect terms order by order in epsilon, right? So the first order is things that are proportional, that are order 1, that has no epsilon. This is only that, and this gave us this equation. What will be the second term?
Everything plus epsilon.
It is this and that. The terms that are proportional to epsilon to the power of 1. So we are going to get y1 double prime is what?
Y naught f.
Is f of x times y naught. What will be the third equation?
Y double prime. Y3 double
Our things that are proportional to epsilon squared.
prime. Y2 double prime.
y2 double prime is equals to
Y1 f.
f of x times y1. Okay?
We know the y0, y not.
Wait, this is it, right? Just to make sure that we have the correct colors. Are you with me?
Yes.
Good. Now, and so on and so forth. So it's very easy. So in general, you can see immediately that yn double prime will be equal to f of x times yn minus 1. That's it. And since we know yn minus 1, because we solved it in the last, right? So we have to solve, actually, since we know that, and we know what f of x is, we have to solve a very simple inhomogeneous linear equation at each step. Relatively simple. Relatively simple inhomogeneous linear equation in each step. There is only one important thing that is quite confusing, so we have to grasp it strongly, right? The question is what we are doing with the initial conditions. So, very important, because then people are getting confused with that like hell. Remember, you put the initial conditions only in the first equation, and all the other equations will satisfy. So I want, actually, my conditions are y naught prime of 0 equals y naught of 0 equals 1, y n prime of 0 equals y n of 0 equals 0. For every n larger than 1, larger than 0. Right? So you put always the initial conditions, the boundary conditions or the initial conditions, only in the zeroth order of your perturbation theory. Why? Because otherwise the satisfaction of the boundary or the initial conditions depend on epsilon. Right? And you don't want that. So this is a rule. You put you enforce the initial or the boundary conditions only on the first solution, and all the others are satisfying zero boundary or initial conditions. Are you with me? Good. So you see this is first, second, third, and this is the general. Now, how do we solve it? As I said, we have the first order equation is that, so the second order equation, this was the zeroth order, and we wrote the solution there, right? So the first order is y1 double prime is f of x times y naught, which is 1 minus x.
1 plus x.
1 plus x. So, and I have to solve this equation, but there is no point in trying to solve this equation because I didn't specify f of x. If f of x is x, for example, as in the Airy function, right? Then we have here x plus x squared, and we can integrate it twice, so we get x squared over 2 plus x cubed over 3, and we integrate it another time, you see? Right? So suppose f of x was x, and f of x was x, then we have y double prime is x plus x squared, which implies that y prime is x squared over 2 plus x cubed over 3, which implies that y is x cubed over 6 plus x plus what? Plus x to the 4th power over 12. Right? However, this I should add constants. Right? So if this is y double prime, then I have here c1, and here I have plus c1x plus c2. Why I didn't bother to keep the constants? Because of the initial conditions. Because the initial conditions are telling me that these are 0. Okay? So this will be the general solution. So you see what I did? I simply did 2 integrations. So in general, I can use it symbolically. I can say that now y1 is the integral from up to x, from 0 to x, dt1, the integral dt2 from 0 to t1 over f of t2 times 1 plus t2. You see, this is just symbolically exactly what I did there. The zeros here are because of the constants are 0. Okay? So I solved for y1. For example, if f of x is x, this is the solution. Okay? Now, can you tell me what will be y2? So you see, I already have the general form. So y2 double prime is f of x times y1. So all I have to do is to write. Now it starts becoming long, but you only have to understand the general principle. I have integral from 0 to x dt1, integral from 0 to t1 dt2, over f of t2 times integral from 0 to t2 dt3, integral from 0 to t3 dt4, over f of t4 times 1 plus t4. This is the trick, and I can do it again and again and again and again. Okay, this is in the special example. You can play with it in this special example, but this is a general trick. Okay, and once I know how to do these integrals, I can calculate everything to every order that I want. Okay, now here comes the question. Before we did it, it was way simpler to do it in local analysis, but we said we have a problem. What was the problem with the local analysis?
Radius of convergence.
Radius of convergence. It cannot converge out of the radius of convergence of the Taylor series of F. What will be the radius of convergence of this garbage?
Everything.
Okay? So suppose I want to do it from up to x equals 5. Right? 5, so if f is, right? Suppose f is 1 over 1 plus x. Okay? And I want to do it up to x equals 5. Is it going to converge? We have seen that the local analysis will not converge. What about the global analysis? Okay? Why I'm calling it global? Because the small parameter is epsilon, is not, right? Is it going to converge in the global analysis case? The answer is yes, it will. And although we cannot solve these horrible integrals, at least we can bound them. Because if now I want to calculate, I have, yes, this is x and this is f of x, and I want to calculate it between 0 and 5, so to speak, right? Or any other number. 5 is just an example. Then, here is the trick. I will look for, so suppose this is f of x, okay? I will look for k. What is k? חסם עליון, upper bound. The upper bound, right? And then I can say that clearly yn of x, right, is smaller or equal to k to the power of n. What is this? This is this f and this f. Just replace them by k, right? It cannot be small. It cannot be larger than that. This is an upper bound, right? K to the power of n times 1 plus x times the integral 0 to x dt1, 0 to t1 dt2, 0 to t2 dt3, blah 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 blah, up to, here we have 1, 2, 3, 4, so it will go up to 0 t of 2n minus 1 dt2n. I simply swallow out the constant of the integration, and what I have is just integrals about 1. Now, what is this integral?
It's like a fat integral.
No, but no, it's a very simple. Okay, look at the first two, right? The first two is what you get for y1, right? So if this is x, if this is, this is 5, right? Or whatever number that you want, right? And this is 5. This integral, you can look at this as as x, right? And this is t1. You see, t1 is you have from 0 to x, and for t1 that is smaller than t2 that is smaller than t1. So the integral on t1, the integral over t1 runs from 0 to 5. The integral over, maybe I didn't plot it correctly. So this will be t2, and this will be this will be t1, and this is t2. Yes. So t2 is smaller than t1. So actually, it's the area of this integral, which is simply 5 squared over 2. Right? You see? And in general, the solution for this integral is what I call 5, I will call it x naught now. Just to, and here of course it's 1 plus x naught, because I take it outside again, I'm taking an upper bound. So 1 plus x is always smaller than 1 plus x naught, and f of x is always smaller than k. So I have k to the n, I have 1 plus x, and I have this. Now this will be x naught to the power of 2n divided by 2n factorial. Right? Which 1/2 is simply when you plug n equals n equals 1. Right? So for n equals 1, you have x naught squared divided by 2. And so on and so forth. So, okay. So what we obtained, we have discovered now that yn of x, the nth power in this power series, right? We have a power series, y is equal to sum of from n equals 0 to infinity of epsilon to the n, yn of x. And yn of x is smaller or equal to k to the power of n, 1 plus x naught, times x naught to the power of 2n divided by 2n factorial. For any finite x naught, what we have here is something that is going exponentially, and below we have something that is going like n factorial. So this will go to 0 for any finite x naught when n goes to infinity. Which means that this series will converge for every finite number. We can go, of course we will have to take more and more terms. But if you want me, if I have infinite calculation power, like as I said, Laplace demon, then I can calculate the function up to x equals million, x naught equals million, x naught equals billion, whatever you like.
If you would like to integrate over whole space, how does you take the limit at the end? If you would like to do the integrals in whole space, like you have bounded up to k, right? But can you, at the end, let's say, take the limit to k what goes to infinity to say that you don't have any cutoff?
No. X naught is the cutoff. X naught is k is just no, I don't understand actually.
Okay, so you have what is k in this?
I'm not trying to tell you that this is a practical method. All I want to convince you is to do this horrible procedure will work for every x. Even if you have f, which is 1 over 1 plus x, and we want to calculate it up to x not equal 25, you can do that. Yes?
Every order of epsilon has its own radius of convergence?
No, the radius of convergence for every epsilon is infinite.
Okay.
This procedure have infinite radius of convergence for every epsilon.
So how we know when to stop developing for more orders?
When you intuitively, when you see that it becomes smaller and smaller, then you stop doing it. When you're a physicist. Okay, good. So this is essentially I went to this example, although it's not so practical, just in order to give you the impression of what's the difference between global and local analysis. Right? So while in local analysis, where the small parameter was a distance from a certain point, in global analysis we put epsilon and the important parameter is the distance from, epsilon is our small parameter. But now if the thing converges, then we can put back epsilon equals 1 and solve the equation we started with. Okay. Now, perturbation theory may be either, this is perturbation theory. Perturbation theory may be either singular or regular. Perturbation theory is regular when the solution for finite epsilon, right? So if I'm taking the solution for y as a function, y is a function of epsilon, right? and I'm taking epsilon to 0, it converges to y naught. Perturbation theory is this is a regular. Perturbation theory is singular when this is not the case. So, for example, which is actually I already gave this example in my first lecture, but now we are. So I'm giving some. How do I? No. So, X. Okay. Suppose I'm looking at this equation. Again, epsilon is a small parameter. Okay. What are the solutions when epsilon is 0? Again, I did very similar example in the first lecture. I'm just doing slightly different example in order to not to do exactly the same. But the morals are the same morals. But now I want to look at it from a from a perspective of what we have learned so far. So if I'm taking epsilon to 0, what I will get is a glorious equation x squared equals 8 that have how many solutions? 3. What are the 3 solutions? The 3 solutions are 2, clearly, x cubed over 8, yes, 2 cubed is 8. And I have 2 e to the 2 pi I over 3 and 2 e to the minus 2 pi I over 3. Right? These are the 3 solutions. Yes. The central theorem of algebra or whatever. Okay? Now, question. If I will solve it for a finite epsilon, and then I will take epsilon to 0, am I going to recover this solution, the red solution?
Again, what is the question?
Sorry?
Ask again. Can you repeat the question?
Yes. When I took epsilon to 0 before solving the equation, I got this, right? These are the 3 solutions. So this is, if you want, 3 solutions for x when epsilon is 0, right? Now I can solve this equation and find x as a function of epsilon. Then I will take epsilon to 0.
Well, it should, because if we see how y it's epsilon to the 0 times y0, which, and then all the others are epsilon to the 1, epsilon to the 2, epsilon to the 3.
No, but I will write now x. I will write x as sum of epsilon to the n xn. Same way. I will solve for that to infinite order, right? And then I will plug epsilon goes to 0. So I will keep only the first order, right? Am I going to recover this?
Yes, because we will get the same equation.
Answer, not quite. Why not quite? Because this equation have how many solutions? 6. And this equation has only 3. So it cannot be the case that all the 6 solutions will converge into 3.
Why not?
So let's remind ourselves what we should do now, right? So we assume that epsilon is small, right? And okay, so what I wanted to do, yes. So as epsilon goes to 0, what should I do? Remember from the first lecture? I want to analyze now the behavior of this equation as epsilon goes to 0. What I'm going to do?
So you expand the x, right?
Find the 2 terms that are dominant.
Good. Thank you very much. Dominant balance. I would like to. I assume already. Although I have here 4 terms, if there is no very bad miracle by some evil Gamad Rasha, I would expect only two of them to dominate the behavior as epsilon goes to 0, right? And then I should check which one is consistent, right? And because, so I have many options to check, and I don't have time, so I will tell you the final answer. The final answer is that epsilon squared x to the 6 is asymptotic to x cubed at epsilon goes to 0. You can check all other options and see that they are not wrong. Now, this option implies that x cubed is asymptotic to 1 over epsilon squared as epsilon goes to 0. Which means that x is going like 1 over to epsilon, sorry, x is going to epsilon to the minus 2/3. Okay? Now you see the trick. Since x is going like epsilon to the minus 2/3, where as epsilon goes to 0, what's happened to x? It goes to infinity. And therefore, it will not converge to one of these solutions. So the solutions you get from here are not something that will converge to this solution. So this is why this is a singular perturbation theorem. Okay? So what one can do, again, I did everything in the first lecture, but now I'm first of all, you have to check for consistency, right? And you can see, because this is epsilon times x to the 4. X to the 4 is epsilon to the minus 8/3. And if I multiply it by epsilon, it's epsilon to the minus 5/3. As opposed to x cubed, which is 1 over epsilon squared, which is much larger than epsilon to the minus 5/3. And of course, this term is also negligible, because it is not going to infinity. Okay? So, what we can use here is to, we will write the way to proceed. Again, I did everything in the, I'm saying it every 2 sentences or whatever. I will define z as, or I will define x like z times epsilon to the minus 2/3. So when epsilon goes to 0, x goes to infinity, but z is still order 1. Z is still order 1. And then if I will rewrite the equation, what I will find? I will find epsilon squared times z to the 6 times epsilon to the minus 12/3, or to the minus 4. Minus epsilon times z to the 4 times epsilon to the minus 8/3. You see, I'm just picking the minus z cubed epsilon to the minus 2. Okay, you see? Plus 8 equals 0. Now, what I'm going to do is to multiply everything by epsilon squared. So this will give me z to the power of 6 minus epsilon. I multiply everything by epsilon squared. So here I have the 1. Here I have
1/3.
epsilon squared, so I have a minus
1/3.
1/3.
minus 5/3, yes, epsilon to the 1/3 times z,
Yeah, z to the 4, right?
z to the 4, okay, of course, minus z cubed plus epsilon squared times 8 equals 0. Ha! This is a regular. Now the perturbation theory becomes regular. Right? Now, this equation, first of all, I can take epsilon equals 0. And now you see that this equation, when epsilon goes to 0, when epsilon equals 0, is z to the 6 plus minus z cubed equals 0. So it will have how many solutions? 6. You see? When epsilon goes to 0, I will have 6 solutions. What are these 6 solutions? So for epsilon to the, if I'm taking epsilon to 0, I have z to the 6 minus z cubed equals 0. So I have 6 solutions that are 0, 0, 0, right? 1 e to the 2 pi I over 3 and e to the minus 2 pi I over 3. You see? And now, around each of these solutions, I will have a regular perturbation theory. Right? So for example, let's take, by the way, what are these 0, 0, 0? These were the two,
The ones that went to infinity.
the ones, no.
First.
Note that this is z. And all this should be multiplied by epsilon to the minus 2/3. So every finite number will go to infinity, and those numbers that are not going to infinity will be here and will emerge only in the second order in the perturbation theory. Right? So for example, now let's try to find the correction to that. Right? I'm starting with 1. Okay? Now clearly from the structure of this equation, I see that z will be 1 plus epsilon to the minus 1/3 times z1.
Okay.
And the question is, what z1 is going to be. Right? The general solution for z is z equal for sum from n equals 0 to infinity of epsilon to the minus n over 3 times zn. Okay? To the minus? No, sorry, to the plus. This is also plus, of course. Yes? This is a general solution. So if I will plug it here, for example, for this one, right? Then I have 1 plus epsilon to the 1/3 z1. And let's plug it into this equation, right? And now, if I will calculate it to 0th order in epsilon, okay, let's write it. So z to the 6 is what? Is now 1 plus 6 times 12 times epsilon to the 1 to the 1/3 times z1. You see why this is z to the 6? I kept only the first term, right? Because I don't want terms that are of higher order than epsilon to the 1/3, right? And now I have minus epsilon to the 1/3 times z to the 4, but for the z to the 4 I should take only the 1, because the next term will be higher order in epsilon. So I have epsilon to the 1/3, that's it, times 1. And then I have minus, again, 1, and minus, I have here 3, so 3 epsilon to 6 epsilon to the 1/3 times what? Times z1 cubed. And then I have something that goes like epsilon squared. It gives me no contribution. It will give me contributions only to the 6th order in the perturbation theory.
Okay.
You see? This should be 0. Okay? So the 1 cancelled with the 1. Why? Because this is by construction. Because this is that. Right? The 0th order gave me 1. And now I can say that to first order in epsilon to the 1 cubed, I have sorry, this is z1 and this is z1 not cubed because I expanded. Right? This is z1. So z1 times, so I get that 6z1, yes, is equals to 1. So z1 is equals to 1/6. One what's going on? 3. Why 3? Sorry. This is 6. I don't know why I multiplied by 2. This is 6, and this is 3. So I'm getting 3z1 is 1, so z1 is 1/3. So to first order in perturbation theory, I can say that one of the solutions, z is 1 plus or minus, I guess it's plus, 1 plus, yes, plus 1/3 times epsilon to the 1/3, right? And if I want x, I should multiply it by epsilon to the minus 3, yes, so the x is epsilon to the minus 2/3, that goes to infinity when epsilon goes to 0, plus 1/3 epsilon to the minus 1, and so on and so forth, right? And so now, to find the solutions that we find before, like the 2 here, this 0 is actually 2, right? Because it's 0, right? So I have to, but I will have to calculate it, I think, until the 6th order in perturbation theory, because I need the 8. I don't get it without the 8, and the 8 is here. It's multiplied by epsilon squared. So if my perturbation theory is 1/3, then I should get 0 in the first 5 iterations, and then I should get 2. That will be the. So this is a singular perturbation theory for x, but regular perturbation theory for z. Right? Another moral from all this is that when I'm getting singular perturbation theory, I'm getting it when I will get a singular perturbation theory when the coefficients of the highest order or the highest derivative is the parameter that goes to 0.
Right.
That's the general scheme here. And here you can see why it comes about, because when epsilon goes to 0, I'm losing solutions. Good? Okay. Fine. So,
It's like when in a normalization group you don't have this solution go to infinity, they flow away.
I'm not sure that I know what you're thinking about.
Okay.
Okay. So now let's start to speak about perturbation theory in the case that we all know and hate, namely perturbation theory for the Schrödinger equation. Okay? So, but of course we are not going to write h bar squared over 2m and all these ugly factors, because this will make our life horrible. We are going to consider the schematic problem y double prime plus v of x y plus w of x y equals e y, right? When we know the solution, so let me write an example. So the example is minus y double prime plus x squared over 4y plus x fourth over 4y equals e y. Right? What is that?
Harmonic oscillator.
No. It will be harmonic oscillator without
No,
the
anharmonic oscillator.
anharmonic oscillator. Right? An oscillator with both something that is linear in the displacement and something that is cubic in the displacement. Like x dot is minus x cubed. Okay? So this is an anharmonic oscillator. And nobody knows what's the solution for this equation. Right? It stands for a while. Nobody knows. Okay? However, to proceed, we want to, yes.
Does it know that you can know this, like it's possible to know the solution, or we know that we cannot know the solution? Like
No, there is no,
Exact way.
in general, there is no way to prove things like that positively. By the way, in what sense you are saying that we know the solution of the harmonic oscillator? Just because we have a name for the function. So here you can define this function to be, who knows? Yes, Archimedes functions, and the Archimedes functions will be the solutions of the anharmonic oscillator.
okay.
And so the idea is not well defined, so to speak. So again, what we are going to do, we are going to put an epsilon here, or equivalently, I would like to put epsilon here, and to solve in powers of epsilon. So I have to put the epsilon where? In a place that when I'm taking epsilon to 0, I know the solution. Otherwise, I always have to know what the solution of y naught. Otherwise, I have no way to proceed.
It's like quantum mechanics 2, right?
Hmm?
It's just like quantum mechanics 2 that you have the harmonic oscillator and then put that
Yes,
small-
yes, so this is, I mean,
Exactly that.
exactly that. So I assume that I know y naught of x. So, okay. I assume I want to write y of x as, and by the way, I have also boundary conditions, which usually in the Schrödinger equation, it will be y of minus infinity equals y infinity equals 0. Standard. Yes? So I'm going to write y of x as a sum from n equals 0 to infinity of epsilon to the power of n times y n of x. And to do the same trick that I did before, I can solve for y0 I have a solution, and I will turn the crank and get more and more solutions. More and more powers in epsilon. You see? That's perturbation theory. Okay? Now, so here, what will be the equation for y naught? Y naught will satisfy minus y naught double prime plus x squared over 4 y naught equals e y naught with the boundary conditions 0 at 0 at 0 at 0 at plus minus infinity. Okay? Now, let's make sure that we know the answer. So my claim is that y naught in that case is e to the minus x squared over 4 up to normalization. I don't care about normalization. Yes, so the unnormalized y naught will be that. So y naught prime, if I'm taking derivative with respect to x, I'm going to get minus x over 2 y naught. You see? And therefore y naught double prime is x squared over 4 y naught. That happens if I'm taking the derivative of the y naught here, right? It will throw out another minus x over 2. Minus 1 half y naught. And if I plug it here, right? So I can say that minus y naught double prime is minus x squared over 4 y naught plus 1 half y naught. And then I am adding plus x squared over 4 y naught. And you see that this cancels with that. And I can say what the other thing I can say. What is E naught? What is E naught? What is the ground state energy? E naught is 1 half. Right? So in the normalized unit of blah blah blah, h bar m, everything is 1 or 1 half or whatever, you get that, one gets that, right? One gets that y naught is e to the minus x squared over 4, and E naught is 1 half. Okay? And now you can go to another Schrodinger equation with whatever thing you want to put here, as long as you have a solution for this. Yes? You know what y naught is. Y naught is a solution where with V but without the W. Are you with me? Okay? Good. Now, here we have a little problem. Why? So we want to plug this into here. Let's write the equations. So the first equation will be minus y naught double prime plus v of x y naught equals e naught y naught, which is exactly what it did there with the specific v of x, and we assume that we know to solve it with the boundary conditions. Okay? What will be the next equation?
-1.
Now I'm collecting this is when I'm collecting only terms that are order
Epsilon 0.
1, epsilon to the power of 0. Now I want to collect only terms that are order epsilon. What should I do?
It's y double prime equal to the
I have minus y1 double prime
equal to
plus v of x y1, right? Now here I have an epsilon, so I will have plus w of x y naught equals to,
EY1.
okay, now remember that we are not, this is not the only series, because the ground state of the is changing, right? So when we're speaking about E naught is actually again sum from n equals 0 to infinity, right? Of epsilon to the power of n times
En.
E tilde n.
It's EN, not EN.
No, okay. This is E. Let's keep, but this is the ground state energy. I don't want, okay, I want to put here E naught. This is a different story. There is the orders in the perturbation theory and the levels of the energy, right? So I'm speaking about this. This is okay. So maybe I should. Yeah. Okay. Here. I mean, in general, there are many solutions to that, right? Because you can multiply this by Hermite polynomials, and then you will have 1/2, 3/2, and so on and so forth, right? So this is E naught in the sense that it's the first, it's a energy of the unperturbed problem, but also in the sense that it's a ground state. But let's decide about from now on that we are speaking only about the ground state. Okay, so E is that's the energy of the ground state. Maybe I should call it E ground state or something, but right. This is the energy of the ground state, and this is that. So when I'm going here, you see, I have a problem. Why? Because now I have,
y1 or y0 there?
So you have
I'm collecting all terms that are order epsilon.
two
Okay.
terms.
So I have two terms. Good. What are the two terms?
It's the zero term in energy. Let's say
E tilde naught
0, y
times y1
1, and plus
plus
epsilon 1,
E
y
1
2.
tilde times
Y0.
y naught. And so on and so forth. It will appear in every term in the perturbation theory. Now, structurally speaking, what I obtained here, remember that I know what V of x and W of x, and I already calculated E tilde naught. I already calculated, right? Maybe here I will also call it tilde. Just to have the same notations. So I already calculated E tilde naught, and okay. So just formally speaking, what I have here is an equation of the form minus y1 double prime plus v of x y1 plus E naught tilde y1 equal to E1 tilde y naught minus w of x y naught. Okay? Okay. Now, if I know what E1 tilde is, then this is an inhomogeneous linear equation. However, I don't know what E1 tilde is. I have to solve for two things. I have to solve for E1 tilde, right? What are the unknowns here? The unknowns are E1 tilde and Y1. There are two unknowns, and they depend on each other. I don't know what E1 tilde is. This is the first problem, and for that reason I cannot solve it.
The last term in the left-hand side is with a minus, right?
Yes, of course. Thank you very much. So I don't know what E1 tilde is. This is my first problem. My second problem is that even if somebody will tell me what E1 is, I am still in trouble. Why? Because this is an inhomogeneous linear equation. So I need three solutions. One of them is a particular solution of this equation with homogeneity, but also, in order to satisfy the boundary conditions, I need the two homogeneous solutions. But here, I did find only one homogeneous solution. There is another one that do not satisfy the boundary conditions, but it can interfere here. So we have a big problem. Okay? This is why perturbation theory in quantum mechanics, which is the only perturbation theory that you become familiar with after having after the first degree, is the most complicated of the perturbation theories, because in every step we have to calculate two things. We have to calculate the next energy, the correction for the energy, and we have to calculate the new wave function. Okay? Fine. So here is the trick. The trick is called reduction of order. And reduction of order means what is reduction of order? I've forgotten to tell you that this is another lecture in which we have one of three in which you have complicated calculations and you have to try to see the forest through the trees. Okay, so the trick of reduction of order is to write y1 that we don't know as y0 times f1. Which is clearly f1 is a function of x, right? So no problems. It's, okay. Now, so we want to plug it here.
Okay.
And when we plug it here, we get minus. So we have to take second derivative of that. So we have y0 double prime f1 minus 2 y0 prime f1 prime minus y0 f1 double prime. This is just a second derivative of that. You see? And now we have plus v of x y0 f1 minus e0 tilde y0 f1 equals E1 tilde y naught minus w of x y naught. Okay? So we took something and make it much more complicated by, however, note that this plus this plus z is what?
0.
0. Because this is the original equation. You see? So these three terms goes out, the red terms, and what remains is an equation for f1 that I can write in the following manner. Okay, so I have only these two terms in the left-hand side of the equation. And these two terms I can write as y naught squared f1 prime minus. Because if I'm taking the derivative here, I will get 2 y naught prime. And if I will get, no, sorry, I forgot it. I have to multiply everything by y naught. So I have minus 2 y naught prime f1 prime minus y naught squared f1 double prime equals to e tilde e1 tilde y naught squared minus w of x y naught squared. Okay? And now this, the left hand side is, this is minus y naught squared f prime prime. Because now if I'm taking the derivative here, I have 2 y naught prime. And if I'm taking the derivative of the f, I'm going to get f double prime. You see? Just to remind you, okay, no, okay. And now the next step, so we have this. Let me erase it here. Okay, doesn't matter. And now I will integrate from minus infinity to infinity. Okay? So what I will get is E1 tilde integral from minus infinity to infinity over y naught squared dx is equal to the integral from minus infinity to infinity of w of x y naught squared dx. This is this, goes to the other side, minus the integral from minus infinity to infinity of y naught squared f prime dx.
So the last term is 0.
Exactly. So the last term is 0. Because the last term is simply minus infinity of y naught squared f prime. And I assume that y naught goes to 0 as plus minus infinity. So this term goes away. And what we obtain is a solution for E1. The solution for E1, if you remember from the course in quantum mechanics, they taught you to first find the correction to the energies and then find the correction to the wave function. So this is exactly that. So E1 tilde is the integral from minus infinity to infinity of w of x y naught squared dx divided by the integral from minus infinity to infinity of y naught squared of x dx. This is a normalization.
This is 1.
Yes. If you work with normalized wave functions, this is 1. And what you get is simply the expectation value of the perturbative potential in the wave functions of the unperturbed potential. Right? That's the first order perturbation. This is what everybody are doing. Fermi golden rule and blah, 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 blah. And usually this is where we stop, right? But we can continue because now that we know A1 prime, we can calculate Y1
using F1.
because now, yes, so we can calculate f1, right? And we can continue that. And now there are, but now of course it becomes yes, because now we have this, right? And we know y1, so now we have a simple equation, right? We know e1 tilde, and we know that. So we can write that y naught squared f1 prime minus is equals to the integral over e1 tilde y naught squared minus w of x y naught squared, right? dx. This is one integration up to x, and the t say, and then we have another integration. So now we can solve it by two integrations. For this, okay? And it yields, but now, okay, this is only first order. Now the second order, third order. So in the book you can find very complicated equations for the nth order. Now I can't say that I can write them on the blackboard, but I think there is no point in doing that because I'm not doing any example with it. So it's just, if you want, please take notice that in the book there are solutions for everything. Okay? Instead of doing that, what I will do now is to go to this example, to the example of the harmonic oscillator. And I will show you that in this case, it's much simpler. Okay, now why it's much simpler? So instead of writing all the things again, I would like to start here. Right? Let's write, no, I would like, no, I would like to start here. It's the same thing, right? I would like to start here. So for the harmonic oscillator, what does it mean?
We know the function there.
Why not?
We know why not.
Right? For the harmonic oscillator, so we are going to write minus y naught squared f1 prime, f1 prime prime, right, is equals to e1, no, sorry, this is good, but I would like to start here, one step before. I would like to start here. Okay, so I would like to start here. Of course, I'm not going to take the red terms because they are gone. They're gone. Okay, so what do I have? I have minus 2 times y naught prime. But remember, y naught prime is minus x over 2 y naught. Remember?
Right. Yes.
Right? This is what I'm going to, which is specific, of course. This is specific to the harmonic oscillator, right? So we have minus 2, so plus 2x over 2 times y naught times f1 prime. You see, this is this term, where I have a minus sign here. Now I have minus y naught f1 double prime is equal to e1 tilde times y naught times f1. Sorry, no. This is e1 tilde times y naught, which is this term, minus x to the fourth power over 4, which is the w in this case,
Okay.
times y naught. And now you see that because of this property, we are in a much better place. Why?
Why not?
Because the y naught cancels out, right? So we take this, and that to have, and we find out a very simple equation: x f1 prime minus f1 double prime is equals to e1 tilde minus x to the 4 over 4. That's it. Fantastic. Now, okay, and by the way, wait. Okay, I'm in troubles. Good. So how to solve? Now I have to solve for E1 and for F. Again, I'm still in the same structural problem. I have to solve for E1 and I have to solve for F. Right? However, since we have here only derivatives and powers, right? I know that the solution must be of the form f1 is a plus bx squared plus cx to the 4. It's a polynomial of fourth order with only even powers. Right? Maybe yes. Let's write it like that. So let's plug it here. What we are going to get? We are going to get, so f1 prime, let's write it. f1 prime is 2bx plus 4cx cubed, and f1 double prime will be 2b plus 12cx squared. So this equation becomes 2bx squared plus 4cx to the 4 minus, what is f1 prime? A double prime minus 2b minus 12cx squared is equals to e1 tilde minus x cubed x to the 4th power over 4. Okay? And now we have to calculate it term by term. Right? So if we are looking for constants, we have minus 2b equals e1 tilde. Right? So e1 tilde is minus 2b. Is that an improvement? Not yet, because we don't know either, each of them. Right? However, we have here, now what about the x to the 4? We have these two terms. So 4c must be equal to minus 1/4. So I know c. c is minus 1 over 16.
And 2b is
And now the third thing will be this and that. So 2b must be equal to 12c. So c is equals to, so b is 6c, but we already found c. So b is minus 6 over 16, which is minus 3 over 8.
Right.
Okay? And this, so we already found what?
E.
E1.
We have to plug
E1.
E1.
E1. So E1 is minus 3/4.
With a plus, right?
E1 is plus 3/4. So we know that the ground state energy of the anharmonic oscillator will be 1/2 plus 3/4 times epsilon. That's the first correction to the okay, I'm taking extra 5 minutes because next week we have no lecture and I owe you already 5 minutes from the last okay, I will pay my debt. And we know also the wave function, because this is f1 is defined as the wave function. f1 times y naught is a wave function. So actually what we are finding here, no, okay. So the wave function will be what we have found. We found B and C. What about A? A plays no role, right? Because this is just a constant. I mean, it's like multiplying the wave function by a constant. Okay? So, okay. So we have, yes, A plays no role. Yes. Okay? Maybe I should start with only B and C and not A, right? So we found the wave function and we find the right, the wave function, you know, y will be e to the minus x squared over 4 plus epsilon times e to the minus x squared over 4 times f1, which is b, and b is
minus 3 over 8.
What?
3 over 8.
B is minus 3 over 8 x squared, and plus c is
Minus 1 over 16.
c is minus 1 over 16. Okay, the global minus sign doesn't matter. No, it does. Yes, I have minus here. X to the 4. Yes.
The A is exactly what we get rid when we do the reduction of order. Right?
Yes. So this is the solution, the first order solution for the harmonic oscillator. Now the trick is that you can do that for very easily to any order of imperturbation theory, provided that you to any order in perturbation theory. But now in the second order in perturbation theory, what you are going to get is something like so the second order will be x f1 prime, f2 prime, sorry, x f2 prime minus f2 double prime, right, is equal to x to the 4 over 4 f1, sorry, f1, yes, that we already found. Something I don't like here. Okay, minus e tilde 1 f1, I guess. Yes, f1 minus e tilde 2. So it's again a function of the same type. Okay? And in order to solve it, what you need to do now, however, is because f1 is now have x squared and x cubed, so now we are going to have here x to the 8, right? Because f1 is minus 3/8 x squared minus 1 over 16 x cubed, x to the 4. So this one will be x to the 8. So now the f2 will be bx squared plus cx to the 4th plus dx to the 6th plus ex to the 8. Right? And plugging that and making but it's all algebra. Right? You know in advance what will be. You have to increase the polynomial, the degree of the polynomial by 2 in every step, and it's all algebra. And you can mechanize it using whatever Maple, Mathematica, or whatever software you want to deal with, and you can calculate very easily. I mean, after spending some time, or after asking the ChatGPT to write for you the script and putting it in Mathematica, then I mean, you hit the bottom and you get 40 orders in perturbation theory without any detectable effort, right? So, and this is actually working for every perturbation. So if I will put here instead of x to the 4, x to the 6, it will also work, right? It's going to work for any perturbation with a potential that is maybe written as a sum of simple parts. Okay? Okay, fine. So I have extracted also exhausted the 5 minutes that I have tried to borrow from the next lecture. So this is that. I don't really know if I want. Yes, I want to add a few things. So next time I will add. But it was important to me to wrap the perturbation theory, even the quantum version of it, within this lecture. And happy Hanukkah. Have fun.
Thank you.
Next week, no lecture?
Next week, no. Yes.
מתי, איזה ימים יש?
בחנוכה אין הרצאות אחרי 4 אחרי צהריים.
בחמישי.
זכינו או לא זכינו?
מה?
חמישי.
הפסדתם הרצאה.
אין הרצאות ואין תרגולים גם? כאילו
אין כלום, אין כלום. אחרי 4 אחרי צהריים.
כלום.
עד 4 הכל כרגיל, אחרי 4 אין כלום.
החמישי הבא.
כן.
הסיכומים של ההרצאות, אתה יכול לשים לזה או שאתה לא...
אני יכול לשים, יש פה עוד כל מיני טעויות קטנות, אבל אם אתה רוצה, אתה יודע מה, שלח לי מאימייל, אני אשלח לך. אין לי בעיה.
אז כל ההרצאות של הרב קוק.
כן.
שלנו.
אם אני עושה טעויות,
מה?
אם אני עושה טעויות, זה מה שאני רושם.
בסדר, אתה אומר, אוקיי, אתה מקווה שזה לא באותו מקומות.
תודה.
נרשמת על הקורולייטית?
עוד לא, אבל אני צריך. כן.
אז אתה תגיד.
כן, בטח, זה הכנס של יונתן.
נכון. אתה שם פוסטר שם?
כן, כנראה. אבל אני צריך לעשות עוד פוסטר.
כן.
ואתה?
אני לא יודע מה מדובר.
מה שאבי שלח בקבוצה. 8 בפברואר עד 10.
זה שלך? יש כנס
כנס קורולייטית דייס בעין גידי.
בעין גדי.
בית מלון כזה.
מעניין.
כל הקהילה, כל הקורולייטד פיזיקס בכל הארץ.
כן. מה זה קורולייטד?
כאילו מערכות,
שאלה טובה.
מערכות מורכבות.
אוקיי.
קונדנס מאטר.
אז אני גם שם פוסטר שם. כאילו כבר שילמתי.
כן?
צריך שמישהו ישים פוסטר?
לא חייב.
ראיתי פה אתם עושים פוסטר. במה הפוסטר?
לא חייב.
So there's the...
אתה משלם
יש
מישהו ישים
כנס.
פוסטר?
לא,
זה
אתה משלם.
איזה אחד? יש הרבה כנסים.
לא, יש אחד שקוראים לה Correlated Days.
אוקיי.
וזה בפברואר? שזה קונדנס מאטר, כאילו בכללי. יש גם Quantum Information. משמעותי זה ממש קונדנס מאטר. שם, כאילו, זה... שלוש ימים.
3 ימים גדי?
כן. 2 לילות. כן. זה קצת עייף.
כן, נשמע ככה.
כן. לא יודע אם היית בכנס. זה...
כאילו עכשיו הכל נופל כאילו על הרצאות, ואז היא אומר לי אל תבוא.
כן.
כן.
כן, לא. זה הגיוני.
היה פה איזה כנס בתחילת הסמסטר, נכון?
ה-IPS, כן.
כן, ואז אמרתי לו, כי זה היה ביום שהייתי מלא הרצאות, אז אמרתי לו, כאילו הייתי כזה, תגיד לי באיזה הרצאות אני יכול לפספס בשביל לבוא, אני לא מלא על כלום.
כן, לא. זה... כן. כי גם האמת ש... לא
לא
מבינים כלום.
אז יופי.
אתה בא, אתה שומע כמה דברים שאתה הבנת, כאילו, השלוש דקות. אם הצלחת, הבנת 3 דקות. בהרצאה.
שונה אבל.
אבל כן, זה גם, אני חושב שזה ממש חשוב, אבל אל תרגיש.
זה בעיה זמן.
באמת לא יודע. אבל כולנו, כאילו זה מה שאני אומר.
באמת.
תכתוב זה לוקח.
לא נשאר לכם בו? זהו? כן. חוזר למעלה?
תומר, אתה יכול להתחיל את ההקלטה כשאתה...
שבוע הבא כל השבוע לא לומדים פה?
כמו, אוקיי, יום חמישי שבוע הבא ויום ראשון עוד שבועיים כזה היום האחרון לא לומדים.
שבוע לומדים בגיל.
חוץ מזה כמו, אוקיי, אבל רוב ההרצאות הן אחרי 4, אז כזה 7, כמו ההרצאה היחידה שיש לי חוץ מהסמינרים זה חומרים דומים להגיד שבוע הבא. וכל שאר ההרצאות הן ב4.
לא תרגול שבוע הבא. Dimitri is not happy.
back. Today we will discuss perturbation methods. As a warm-up, we will solve a bunch of polynomial equations. Then we also solve transcendental equations, and in the end we will solve two different differential equations with the perturbation methods. Okay, so let's start with the simple quadratic equation.
Did you start it?
So we need to use the second order perturbation theory and find all the roots of this equation. Okay. So, and we need to compare them with the exact roots. Okay. So let's compute firstly exact roots. We know the formula for the quadratic equation, right? So it's -1 plus minus, there is a 1 minus 4 times 6 epsilon divided by 2. Okay, so let's expand the square root. Okay, so we will have -1, then plus minus 1 minus 1/2 times 24 epsilon. Okay, and then we do the next term. So the next term will be with the coefficient will be minus 1 over 4. So when we do the math, it will be 6. Okay, let's do this, please. So the coefficient is 1/4. Then we need to square this. So it will be 16 times 36 epsilon squared. Okay. So, and we need to divide it by by 2. Okay. So in total, we will have minus 1 over 2 plus minus 1/2, then minus 6 epsilon. Here, 8. So 2. And divided by, so 72 divided by 2. So with the plus sign, plus 36 epsilon squared. Okay. Good. So we know the exact solution. And now let's do the perturbation theory. So we assume that our solution x depends on epsilon, and we solve it with the expansion. Okay. Then we just plug this into the equation and match the terms. All of this in
power plus x naught plus epsilon x1 plus epsilon squared, right? Plus 6 epsilon equals 0. Okay. Now let's match the terms. So what do we have? We have x naught squared, then plus x naught, right, equals 0. So we have two roots, right, for x naught. X naught is 0 or minus 1. Okay. Then we match terms with the epsilon. Okay. So with the epsilon we have here, right, 2 x naught, x1. We also have here plus x1 and plus 6. Plus 6 equals 0. So we can solve this equation with respect to x1. And the answer is minus 6 divided by 2 x naught plus 1. Okay. And because we want to solve the problem up to second order, we need to also match the terms of epsilon squared. Okay. So for the epsilon squared, we have here, right? So x1 squared, then also in this parenthesis, when we do this and this, right, we will get plus 2 x naught x2, and the last term is plus x2. Has to be 0. Okay. And again, we solve this equation with respect to x2. So x2 equals minus x1 squared, and in the denominator is 2x naught plus 1. The same denominator as we saw here. And now when we know all the coefficients of the expansion, we just can write two solutions explicitly. Okay. So the first root, let's use x naught equals 0. So then we have 0, then minus 6, okay? So minus 6 epsilon, okay? Then minus, and we need to plug in here x1. x1 in this case is minus 6, so it's again in the denominator we have only 1, so it will be minus 36 epsilon squared.
This is what you mean by x1 is one solution of x of 0?
Okay, yeah. Let's yeah, because you can. So let's call it I don't know.
A and B maybe. I don't know.
Okay.
Or plus and minus. I don't know.
Okay, well, let's skip and b. X and xb. We take x naught equals minus 1, so it will be minus 1. Then we plug in minus 1 here. It's just with plus 6 epsilon. And the same is here, right? Because here is minus, so we can do the same this one, plus 36 epsilon squared. So these are our two solutions using perturbation theory. Let's compare them with the solutions that we got from the known formula for the second order quadratic equation. So if we take plus sign, right, this minus 1/2 and this plus 1/2 cancel each other, right? And we have
the signs
the
doesn't match
sign,
up.
yeah, the
The
sign.
minus and the
Yeah, maybe
It should be here minus, right?
Yeah.
Should be here minus. Okay, so minus and then it will match. And if we take the minus sign, we have the second. So we can call this x plus and x minus. Okay. Now let's again use perturbation theory to find all the roots of cubic equation. It's x cubed minus epsilon x minus 1 equals 0. So let's do the same trick. Expand the x as a power series epsilon after the second order, and again just plug into the equation and match the powers. So we have x naught plus epsilon x1 plus epsilon squared x2. The third power minus epsilon x naught minus epsilon x1 with a plus, sorry, plus epsilon squared x2. Okay, and then minus 1. Okay, now let's match the powers. So in the first one we have x naught cubed, right? In the second term we don't have any epsilon to the 0 power, so minus 1 equals 0. Okay. How many roots do we have?
3.
3, yeah. So the first one is just 1, then the second one is e to the I 2 pi divided by 3, and the second one is e to the I 4 pi divided by 3. Do these things. Okay, great. So then the next power of epsilon, we have 3x naught squared times x1 from the first term. Okay, then from the second term we have x naught. Okay, and that's it. Equals 0. So we solve this equation with respect to x naught, and x naught is just 1 over 3 x naught. x1 is just 1 over 3x. Okay, and then the second term. So we have 3x naught squared times x2, then plus 3x naught x1 squared. It's from the first one, from the first term. And from the second term, we have minus x1 equals. Okay, and then we just solve it with respect to x2. So from the third one, x2 equals, let's see, so it's x1 divided by 3x naught squared right minus 3x naught x1 squared divided by 3x naught squared. Okay, this cancels out. Okay. So this 3 also cancels out. Let's plug in x1. So we'll have 1 over 9 x naught cubed minus, plug in x1 squared, 1 over, again 9 x naught squared multiplied by x naught, so it's x naught cubed. And you see that it's just the same, so yeah, it's just 0. So at the end of the day, our solution is x naught, then plus epsilon divided by 3x naught, and the second correction is always so, and basically now we can write all of the three solutions. So x, let's call it like x1 is just 1 plus epsilon over 3. The second solution is e to pi over 3 plus epsilon over 3 e minus e to pi over 3. And the third one is e to the I 4 pi over 3 plus epsilon over 3 e minus e 4 pi over 3. Okay. Okay, good. Any questions? Right. Now let's solve the next one. Now we have this equation x squared with some numbers. Okay, 2.0004 x plus you can solve it? No?
No.
No? Okay. And we need to also find the solution equation, compare it to the solution that we know how to derive, right? So let's rewrite this with the epsilon. So we can write it as x squared minus 2 1 plus epsilon x plus 1 minus epsilon. Where epsilon is 0.0002. Some small number, okay? And now let's firstly try to find the exact solution with the known formula, and then we will try to solve it with the perturbation theory. Okay? So, with the known formula, we have plus 2, 1 plus epsilon plus minus square root of 4, 1 plus epsilon squared minus 4 times 1 minus epsilon. Okay, it's numerator and the denominator just 2. Okay. Or I can just rewrite it, all of this without 2. Right? So now let's expand the square root. Yeah. Not expand, but simplify. Okay. So 1 plus epsilon. Okay. Then plus minus. And what do we have here? So 1 plus 2 epsilon plus epsilon squared minus 1 plus epsilon.
Epsilon plus epsilon squared.
Yeah, it's epsilon squared plus 3 epsilon, right? 1 plus epsilon plus minus square root of epsilon squared plus 3 epsilon. Okay. So these are our solutions. Okay. Now let's try to use the perturbation theory to find out the solution, to get the solution in different ways. So x equals x naught plus epsilon x1 plus epsilon x2, epsilon squared x2 plus, and so on. And we plug this into equation. X naught plus epsilon x1 plus epsilon squared x2, all of this squared, minus 2, 1 plus epsilon, here is x naught plus epsilon x1 plus epsilon squared x2, right, plus 1 minus epsilon equals 0. Okay, let's carefully match terms. For epsilon to the 0, we have x naught square. Then, from this term, we have minus 2 x naught and plus 1. Okay. So you can simply rewrite it as x naught minus 1 squared. And x naught is just 1. Okay. So, and it's double root. I have 2 identical x naught. Okay. So let's try epsilon in the first power. So we have from this 2x naught times x1 cross term. From this we have minus 2 times x naught and minus 2 times x1. And minus 1 equals 0. Let's solve this with respect to x1. So x1 should be 1 divided by
1 plus
1 plus 2x naught. Thanks. 1 plus 2x naught divided by 2x naught
minus 2.
minus 2. Yeah.
But I get 2 over 0.
Exactly. What does it mean?
Singular perturbation theory.
Yeah, the usual doesn't work, right? You have that one of the coefficient just go to infinity, right? So that's why we need to use other type of perturbation theory, which is singular, right? So what do you know about singular perturbation theory? Not much. I see.
So you have to make the change of variables, right?
Yeah, basically, then your coefficient goes to infinity. It means that you choose wrong.
The wrong balance, right, in the equation.
Yeah, I mean, this one is just wrong. The wrong expansion for x. You need to use other power series of epsilon. So, and now we will see what's better. I mean, this is wrong. We know that. And now let's try something else. We know that our zeroth order approximation, right? It's still valid. And now we try to find the scaling of epsilon. Okay? So we just use the same x naught. Let's plug in it. So it's 1, and then we write plus delta. Okay? Delta is some function of epsilon. And now our goal is to find how delta depends on epsilon. Find proper scaling for epsilon. We just simply again plug this to to the original equation and use them in balance to find out the proper value of delta. Okay, so let's do it. We have, let's write this way, 1 plus delta cubed minus 2 1 plus epsilon times 1 plus delta squared plus 1 minus epsilon equals zero.
Why is the cubed squared? Shouldn't it be squared and
It should be as this. Yeah.
The first one is
Yeah. So, yeah. That's right. Thanks. Okay, then let's rewrite it. Okay, now we have we need to simplify it, right? So 1 plus 2 delta plus delta squared, this is the first one, then minus 2, okay, then minus 2 delta, minus 2 epsilon, and minus 2 epsilon delta, plus 1 minus epsilon. So plus 2 delta and minus 2 delta cancels out. Also we have plus 1 and minus 2, they also cancel out. This. Okay, and minus 2 epsilon minus epsilon is just minus 3 epsilon, right?
Why the one cancelled out?
Because we have plus 1 and plus 1 and minus 2.
Minus 2.
There's a minus 2 term. Okay. Now, delta, we have delta squared, then minus 2 epsilon delta, and minus 3 epsilon equals 0. Okay. Now let's try dominant balance. Just pick two terms and see if that choice is consistent or not. So let's pick the first two. Okay. So delta squared is 2 epsilon delta, or delta behaves like 2 epsilon. Okay, let's then plug this to the original equation. And see, and we know that epsilon is something small, so let's use this one. Epsilon goes to 0. So the first term, epsilon squared, right?
Mm-hmm.
The second term, epsilon squared. And the third one, just epsilon. And because epsilon goes to 0, we cannot neglect this, right? So it means that this choice is wrong, okay?
So
but you also can understand that that choice is wrong because we already try the power series of epsilon, right? So that means that you can't really, just multiply by 2. You cannot really fix that. Okay?
Right.
So this is wrong choice. Okay, we also have option this and this, but delta will be just a constant in this case, right? So it's not a good choice also. We know that delta has to be some function of epsilon. So let's try the first and the last. Delta squared 3 epsilon, or delta square is square root of 3 epsilon, and that is something new. Okay. So now we need to try the other expansion, right? So the new expansion will be the following. So it will be epsilon to the 1/2 x1 plus epsilon x2 plus epsilon 3/2 x3 and so on. Okay. This is the consistent choice. Okay. So now let's try to find out with this expansion. Let's find out x1 and x2. Okay. Let's fix the powers. Okay. Now we have here 1/2. 1/2. Again, zero order is the same. But in the next order, you will see changes. Okay? So it should be power. Do we have powers of epsilon 1/2? Yes, right? So let's keep the terms there. So epsilon 1/2 we have here, right? So it should be 2x0 x1. Okay. So for this, that's it for the first term. Then for the second term, we also have epsilon to the 1/2 with the coefficient -2 times x1. Right, and that's it. Equals 0. Okay, we can solve this equation. So when we see that x1 should be, so let's
equal to 0.
just a second. 2x. U-turn. Understand? Stop.
Why you take when you calculate the delta there? Why you take that just a positive square?
Oh, it should be plus minus, but the purpose of it to just find the proper scaling for epsilon. I mean, we can. I mean, it's not a problem, but because we found the delta, and we use this x0 1 plus delta, right? So now we know that delta, so it's plus minus 3 epsilon, right?
Mm-hmm.
Okay. So we know it. Need to be very careful with this perturbation analysis. we should get the coefficient of x1 should be square root of 3, right? So we missed the square. Okay, let's try this. Respect to epsilon. Respect to epsilon, we will have x1 squared, right? Then plus 2 x naught x2, and then here minus 2 x naught minus 1, right? Minus 1.
If x1 is 0, then we'll get x2.
No, it shouldn't be 0. It should be square root of 3.
No,
I mean, from the scaling, we found it. From the scaling. So actually, we already found the x1. Should be plus minus square root of 3. Okay, I just cannot find the mistake here. We should also get the same x1, but for some reason I cannot see where is the mistake. So yeah, we can solve it for x2. x2 is 1 plus 2x naught divided by no, it's 1 plus okay. Let's use this equation, and we'll derive all of the coefficients from this equation. So we know that delta in the first order approximation is square root of 3 epsilon. Okay. The next correction will be some x2 times epsilon. Or we can do it in a general way, so we can say that delta is x1 times epsilon to the 1/2, right, plus x2 epsilon. And we can use this equation. Okay. So let's calculate delta. Delta squared is x1 squared times epsilon plus 2x1 x2 times epsilon to the 3/2 plus x2 squared times epsilon squared. Okay, it's delta squared. Then we have the term minus 2 epsilon delta. It's minus 2 x1 epsilon to the 3/2 minus 2 x2 epsilon squared. Okay, and minus 3 epsilon. So now let's match the terms. We have epsilon. So with the epsilon, it's x1 there, right? And this minus 3 epsilon. The only power of epsilon here is this term. Here we don't have any epsilon. So from delta squared we have x1 squared coefficient, and from here we have minus 3. Should be equal to 0. And that's how you can get your plus minus 3. Square root of 3. Okay. Then e to the 3 halves. We have 2x1 x2. Okay. From the delta squared term. From the second term we have minus 2 x1. Okay, and that's it, right? That means that x, we can find x2, right? So x2 just 1. So now we know the proper expansion. So the proper expansion for x is x naught was plus 1, I think. 1 then plus x1 times epsilon 1/2. Okay, so plus minus 3 square root of epsilon. Okay, and then plus x2 is just 1 times the epsilon. This is our solution. And now we see that 1 plus epsilon we have here. And if we neglect the epsilon squared term, we have plus minus exactly square root of 3 epsilon. So again, you can get the same answers from this, okay? But you have to be very careful with all the coefficients in math. So yeah, but you can use delta. Doesn't matter. Okay. Any questions? No? Good. Now, let's look at the next example. So, yeah. So, why do we call this? Why do we split the perturbation theory by 2 parts, by regular and singular? So, when you have singular regular perturbation problem, usually if you plug in epsilon equals 0, it doesn't change the number of roots of the equation. Okay, But then you, if you solve the singular perturbation problem, plug in epsilon equals 0 actually somehow changes the number of roots. So in this example, if we plug in epsilon equals 0, we have x equals 1. So we have 1 root. But if we take epsilon non-zero, we eventually have 2 different roots. Okay? So, and the next problem also about this number of roots. So we have x plus 1 to the power of n equals epsilon x. Okay, and epsilon, as usual, a small parameter. We need to solve this. You see, if we plug in epsilon equals 0, we have x equals minus 1. So, but there are n roots, right? So, but if epsilon is not 0, we have a lot of different roots. So, and we need to find out how we can use the singular perturbation theory in this to solve this equation, to find all of the n roots of this polynomial equation. So, because we know the solution when then epsilon equals 0, basically it's our x naught. Okay, and we want to find out the proper scaling for epsilon to write the correct power series. Okay. So how do we do that? Again, try to do this thing with 1 plus delta. So x naught plus delta. In our case, x naught is minus 1. When we add some delta, it's a function of epsilon. We don't know what exactly function is, but we'll try to find it. And then we plug this x to the equation. So it's just delta to the n power equals minus epsilon plus delta. Okay, so let's try to do dominant balance. Let's try this and this. So delta there.
Delta epsilon, no?
Hmm?
Delta epsilon or not?
Yeah, delta epsilon. Let's try this and this. Okay, and delta then goes like minus epsilon to the power 1 over n. Let's see if it's consistent or not. If we plug in here, this term goes like epsilon, this term goes like epsilon, this term goes like epsilon n plus 1 divided by n. I can multiply this by epsilon and I have this. So, and because n plus 1 divided by n is bigger than 1, it decays much faster than this and this. So, therefore, this choice was consistent. Okay. So now we know that how the delta scales with the epsilon. Okay. And now, let's find it. Okay, so our x is minus 1 plus minus epsilon to the 1 over n. it's our solution. Again, we can also try to find the next correction, but you need to plug in x2 minus e to the 2 divided by, and so on. But that's basically that's the answer. So now I think you have some intuition about roots, about double roots, about triple roots. So if you have double root, probably the proper scaling is this, right? Because 1 over n. If you have a triple root, so cubic, right? Well, that's pretty much it.
This is general, like the order of the degeneracy of the solutions.
Yeah, it gives you the proper scale. Yeah. Okay. Let's see. Yeah, let's try this problem. X cubed minus x squared plus epsilon. Can you guess? Is it regular, singular perturbation problem?
Singular.
Why?
Because if epsilon is 0, so you have another roots of x equals 0.
Yeah. And we know the proper expansion for
1 over
that.
3. 1 over 2.
Yeah. So for for epsilon equals 0, we have x squared times x minus 1 equals 0. And we have in total 3 roots, right? So the first one is just x equals 1, and the other 2 are 0. This is double root. Okay. So for the first root, we will use
No, you
Regular-
have
regular.
twice 1 and 1 0.
3 root.
So you say x equal to 0 is double root.
Yeah, because it is.
Ah, okay, okay.
It's squared. So for the first, we will use regular integration theory, and for the other 2, singular. So let's firstly solve for. Let's go with x naught. So for x naught equals 1. For x naught equals 1, our power series for the solution is 1 plus epsilon x1 plus epsilon square x2. Okay, let's plug this equation. 1 plus epsilon x1 plus epsilon square x2 cube minus 1 plus epsilon x1 plus epsilon squared x2 squared plus epsilon equals 0. Okay. Now let's match terms. So we already know that the solution for the 0 follow. So let's begin the first order. So for the first order, we have here 3 x1 and that's it. From here we have minus a cross term 2x1, right, and here plus 1. So x1 is just minus 1. Okay. So let's do the second order. For the second order, we have 3 times x1 squared, then plus 3 times x2. This is from the first term. From the second term is minus 2x2 minus x1 squared. Okay, now we solve this for respect to x2. So x2 is x2. We need to okay. So it's minus x1 squared. So minus 2, right?
Right.
So we know that the solution for one root is 1 minus epsilon minus 2 epsilon squared. Now let's do the double root. The double root we know also, we already know the expansion. So double root x naught equals 0. We should find solution as epsilon 1/2 x1 plus epsilon x2 plus and so on. So epsilon 1/2 x1 plus epsilon x2 cubed minus epsilon 1/2 x1 plus epsilon x2 plus epsilon squared plus epsilon equals 1. Okay. So the smallest power of epsilon in this term is epsilon squared. So we cannot match this to this. So we need to look at this one. Here we have epsilon.
Epsilon.
Okay. So minus 1 minus x1 plus 1 plus 1 from
Squared. Minus x1 squared.
yeah, that's the point. Thanks. Equals 0. So x1 is just plus minus 1. Okay. So the next one, x to the epsilon to the 3 halves.
You have something?
3 halves. The first one. Right? So the first one, it's x1 cubed. Right?
And that's it. Minus 2x1.
And cross term here. Minus 2 x1 x2, and that's it equals. So x2 is just x1 squared divided by or just 1/2. Okay, great. So now we can write the two other solutions. So plus minus epsilon, okay, and then plus epsilon squared. 1/2 epsilon. And I see that there are two solutions. And the last polynomial equation that we will solve is the following. Plus x squared. Minus 2x plus 1. When you look at this equation, you can immediately say that this is singular perturbation theory. Why? Because if epsilon equals 0, we actually, the order of this equation decreases by 1, so it will have only two roots, right? So let's rewrite it this way. Let's simplify it like this. And we know that if epsilon equals 0, we have just x naught, just 1. Double. So, and now for the double root, we know what is the scaling, right? We can solve it. So x of epsilon is 1 plus x1 epsilon half plus x2 epsilon plus so on. Let's plug in this to the equation. We will have epsilon times 1 plus x1 epsilon half plus x2 epsilon all of this cubed plus x1 epsilon 1/2 plus x2 epsilon all of this squared equals 0. Okay, so the smallest power of epsilon is the first one, right? So from the first term we have just 1, right? From the second term we have no, I think we should.
Is it a double or a triple root though? Since like a third root appears when epsilon doesn't equal 0.
No, in this case, an epsilon equals 0, we have only this equation. So
Yeah.
Just simple double root.
When epsilon doesn't equal to 0, shouldn't it be a triple root? Shouldn't there be
No,
three
it should
roots?
it should be just 3 different
Yeah,
roots. So firstly, let's manage double root, and then I'll show you how to find the third one. Yeah. Okay. Yeah, let's carefully find the powers of epsilon. From the second term is plus x 1 squared 0. Okay. So x1 there plus minus e. Okay. So then the next power 3 halves. With 3 halves, we have 3x1 from the first term, right? And without, and that's it, I think. Then plus, and the second term we cross 2x1 x2 equals 0. So x2 is simply minus 3 halves. Okay. Good. So finally, of the double root, we know these the solutions. Okay. So it's 1, then plus minus I square root of epsilon minus 3 halves epsilon. Okay, now how to find the third one? The third one we'll use dominant balance. So we just simply try to find the proper scalar for the third solution. So again, we look at the original equation. Let's look at this one. Okay. Oh, it's better to look to the original. And to do just regular dominant balance. So let's try the first and the second term. Epsilon x cubed minus x squared. So 4x feels like minus 1 over epsilon. So let's see if it's valid or not. So the first two terms goes like 1 over epsilon squared. And because epsilon goes to 0, they are very big. Okay? While this is just a constant, we can neglect it, and the third term goes like 1 over epsilon, which is also blows up, but not as fast as the first two. So that means that this choice is consistent. Okay, and now it doesn't mean in this case that we need to calculate the x as a power of series of negative epsilon. No, we need to rescale the x. Okay, so we define new variable. Let's call it y, and y is just x times 1 over epsilon. No, should be just times epsilon. Because x goes like 1. Okay, and then x is y over epsilon, and now we just plug this to the equation. Okay. So we'll have epsilon times y cubed over epsilon cubed plus y squared over epsilon squared minus 2 y divided by epsilon plus 1. Okay? And multiply both sides of the equation by factor of epsilon squared. And we'll get the new equation. Y cubed plus y squared minus 2 epsilon y plus epsilon squared equals 0. And now you see that this is again the new problem that we have to solve. Okay, let's do it. For epsilon equals 0, we have basically the same y squared times y plus 1. Okay, equals 0. So here we have double root. And y equals minus 1, single root. So this double root, exactly this one, just for the new value. Okay. So actually we found these two already. So now we focus on this one. Okay. And this just now it's just regular perturbation theory. Okay. So now let's find y as a function of epsilon, so y naught plus epsilon y1 plus epsilon squared y2. Again, plug in this into the equation. And we know that y, let's call it y naught. Okay, y naught. And for y naught equals, then we have 1 plus epsilon y1 plus epsilon squared y2, all of this cubed, and plus 1 plus epsilon 1 plus epsilon squared y2 squared minus 2 epsilon times 1 plus epsilon y1 plus epsilon squared y2 plus epsilon squared. Okay.
It's minus 1.
Minus 1? Ah, thanks. Minus 1. So, epsilon. For epsilon, we have 3 y1 from the first, then from the second, minus 2 y1 and plus 2 from the third. Now we see that y1 is just 1 or minus 2, minus 2. It's minus 2. Okay. And to the second opening. The second order, from the first, we have minus 3y1 squared and plus 3y2. From the second term, we have plus y1 squared and minus 2y2. From the third term, we have minus 2y1 and the last is plus 1. Okay. From this, y2 equals, let's see. So this and this give me minus 2y1 squared, but we move it to the right hand side, so it's 2y1 squared, and then I also have plus 2y1 and minus 1. So there should be 8 minus 4 minus 1, so it's 3. So and therefore y of epsilon is minus 1 minus 2 epsilon plus 3 epsilon squared. Okay, but now we need to go back to the x, right? And we know that x is y over epsilon. So x of epsilon is 1 over epsilon times this, right? So it should be minus 1 over epsilon, then plus 2, and then plus 3 times epsilon. Yeah, that's the third root. And you see what's happened with this root when epsilon goes to 0.
Right.
It goes to
Explodes.
minus infinity. Okay, so yeah, we have only 6 minutes, so let's do the one example of transcendental equation, and we'll finish. Because you're not really solve polynomial equations in physics. I mean, you can, but usually you solve transcendental or in most cases differential equations. Yeah. Sure. Okay, now we have y equals x minus epsilon times sine 2y. We need to find using perturbation theory y. Okay, so as a power series. So now we try to say that y now it's function of epsilon and x. So we have y naught plus epsilon's as a function of x. Epsilon's time y1 x plus epsilon time y2, epsilon squared time 2, and so on. Okay. So let's plug this into equation. So y naught of x plus epsilon y1 of x plus epsilon squared y2 of x and so on equals x minus epsilon times sine 2y naught x plus 2 epsilon y1 of x plus okay, before we're gonna match the powers, we need to do something with this sign, right? I mean, we can match epsilon of 0, right? Why? Because it's just simply x. In the zero pseudo, we just neglect this. We set epsilon to 0 and y equal. So, but for the next order, we need to do something with this sign. So basically, now we have some function, okay? Let's call it 2y naught x plus something small. This is small compared to this. So we can use basically Taylor expansion. Right? So the zeroth order we just write sign as it is. Okay. For the second order we need to multiply the derivative of this function, right, by the difference between these two values. So the derivative of this is just cosine of the same argument, okay, times this. Okay, so now let's match the epsilon in the first power. So left hand side we have y1 of x. The right hand side we have epsilon times this. So the sine of 2y naught of x. And because we know what's y naught, it's just sine of 2x. Now let's do the second order. The second order, left hand side we have y2 of x. Right hand side we have, I think I missed the sign, minus before. So here is the also minus, but 2 y1 of x times cosine of 2y naught of x, or just cosine of 2x.
Shouldn't the minus cancel out?
Yeah, because here we also have minus, right?
Yeah.
So yeah, thanks. It should be plus, right? So 2 sine 2x cosine 2x, and then you see the formula, you can simplify it. Just simply sine of 4x. Okay, now we got the solution, right? This is a mental equation. So the first is just x and plus epsilon, minus epsilon times sine of 2x, and the plus epsilon squared times sine of 4x. That's your solution.
Yeah, in the tutorial you can find one more example with the transcendental equation, with the exponent and square root. And there are 2 examples with the differential equations. So please look at them, because in the homework you're gonna solve this. Yeah. Thank you.
Thanks. Thanks.
Thank you.
Bye.
You know if we need to stop the call?
I think I stopped it.
No, the recording, you did, but like
The Google Meet?
yeah.
Maybe. I just don't know how. I think it's automatic, you know?
אחי, תגיד, אנחנו צריכים לכבות את השיחה גם? או רק את ההקלטה? סבבה.
Okay.
כן. כן, אבל אני אבוא ואלך. אמרתי, אני אבוא ואלך. אני אבוא ואלך. כן, נראה. ביי ביי.
Bye.